Welcome to the lectures on modern digital communication techniques. So, as said in the previous lecture, we have covered modulation and now we are into the receiver. So, we have started discussing about the AWGN channel, which we have discussed in the previous lecture, and then we wrote the expression of the received signal at the receiver when it passes through an AWGN channel, and then we started discussing about the receiver structure. For which we had to recall our understanding of the modulator or the symbol mapper, where we said that the symbol mapper essentially takes a bit stream and produces waveforms, and the job of the receiver is to do the reverse. That means, it has to take the waveform and reverse map it to the bit stream, and therefore, you could define the criteria for designing a good receiver in the sense that you would like to make the minimum amount of error. And then we said that we want to design a receiver for AWGN channel which minimizes the probability of error. So, we will quickly look at some of the things which we discussed in the previous lecture, so that we can continue with our discussion on the topic. So, quickly let us see, we provided a model where there is a transmitter, the channel and the receiver, and noise gets added at the receiver. We also said we will take a look at the ideal channel where channel gain is 1, and effectively it is also known as the additive white Gaussian noise, and we want to design a receiver for a AWGN channel. So, we said let us design an optimum receiver for AWGN channel, and since the modulation does a binary to symbol mapping or waveform, the receiver does the reverse process. And we looked at the received signal R of t, which was equal to the Sm of t, where Sm is the transmitted signal, where m ranges from 1 to up to capital M, that means selecting one of the possible waveforms, and there is noise getting added. We said this is white because the receiver uses a filter which is much wider than that of the signal, and the noise is spectrally white in that portion, and the receiver sees this signal in the time interval 0 to capital T, that means in each symbol interval. And we did discuss about this kind of a figurative representation. This is the expression of the received signal. This we all discussed in the previous lecture, and we described the noise with the power spectral density as n naught by 2, and then we said based on the observation of R in the interval 0 to t, that is a symbol in interval, we would like to design a receiver that is optimum, and we described the meaning of optimum in the sense that it minimizes probability of making error, which we just described once again. And then we looked at the receiver architecture, where we said that the received signal is first demodulated. So, it goes through a demodulator and then it goes through the detector. You have typically studied demodulator in analog communications, and you will see some form of similarity in this as well. So, together it forms the receiver, it takes in received signal, it produces output decision, and this decision is about which of the possible waveforms was sent. This we again revised a few minutes back. And the demodulator, we were discussing about this, it converts RT into n dimensional vector. This is what we had stated. So, that means it decomposes R into R1, R2 up to Rn, where n is the dimension of the transmitted signal, right. So, to explain the dimension of the transmitted signal, we did take a look at the pulse amplitude modulation, which is one dimensional, that means it chooses only the amplitude of the basis function. So, this is the component of the signal on the basis function, that is what we explained. For phase shift keying, we said you could decompose into a I and a Q channel, and you could have projections on the I as well as on the Q, and these are the components on one basis and the other basis. Then we moved on and discussed that there could be a QAM constellation, whereby you straight away have this relationship, that means there is an amplitude in the cosine carrier, amplitude in the sine carrier, and it goes as quadrature amplitude modulated signals. So, in these two cases there are two basis functions, one along the I, that is this one along the Q, which is this one. So, these are the two dimensions that we have looked at. Then we looked at the n dimensional scenario, where we also said that if there is T and there is n1 and n2 dimensions, you could have n1 n2 dimensions in the space. So, you have n dimensional signal, and then we explained finally that if you have R of t, what we are basically stating when we say that R is broken into components, it is basically R of t is projected onto the basis functions and it produces these components of R on the basis functions. So, we should recall that if there is a signal S t and we have f k's as basis functions which span the signal space, that means the signal could be expressed as a linear combination of these basis functions, then you could decompose or you could represent S t in a vectorial form, and this was in one of the particular lectures we did discuss the signal space representation, and that the signal follows all properties of a vector when we break it down into this form. Then we can do vector operations on signals as well, and S k, that is the coefficient or the component, can be computed in a form that is projection of S t on f k. So, that you would do by integration 0 to t S t f k t, where f k is one of the basis functions. And we recalled in case of Emery f s k, this was the transmitted signal and you had to correlate. So, it was basically projecting the signal onto different bases where you have this k as the different frequency components, different signals. So, once you do this projection by virtue of orthogonality, which we got delta f equals to 1 by 2 t, then the projection could be zeros in case of ideal on all other signals. There would be an energy in the desired component when m is equal to k and 0 again on the others. So, that means projection of R t, that means when you break R of t into these components for Emery f s k, ideal case you would get like this. In case of noise, you would be getting some noise components. So, the base signal would look like this. In case of noise, there would be some n 1, n 2 and so on noise components present along all of these. So, this is what we had discussed in the previous lecture. So, moving on, we first look at the correlator receiver, because we stated here that this demodulation can be realized in two ways. One is the correlation based and the matched filter based, and which we will look at in today's lecture. So, when we take a look at the correlation demodulator, what we do is R t, that is the received signal, is decomposed into a series of linearly weighted orthonormal basis functions. Now, this is not new for us, because we have already discussed this thing, that what is meant by decomposition. So, it is similar to S of t being represented as a weighted linear combination, where the weights are the components of the signal on the basis functions. So, now since S of t could be constructed by taking S k, which are the coefficients, along with f k as the basis, here it is the reverse process, that means finding the coefficients for the signal corresponding to the basis function. So, it is a reverse thing, and that is basically projection, which we have explained over here. So, this is the construction of the signal, this is the decomposition of the signal. So, you are breaking down into components. So, instead of S t, we now have, we will apply the same philosophy on R of t, that means we will apply the same philosophy over here. So, we assume that the n basis functions span the signal space. So, this is always there. So, that means whenever we discuss communication systems or when we discuss signals and we are talking about basis functions, if your basis functions do not span the signal space, then what is going to happen? When you expand the signal using whatever limited basis functions you have, you are not reconstructing the signal in its entirety. There would be some amount of error which is left. So, we do not want to do that over here. So, since it is within our control, we can find the basis functions, and in order to find them, we had done Gram-Schmidt orthogonality, by which given a set of signals. So, if you have a whole set of signals from which you could construct orthogonal signals. So, once you have the orthogonal signals, there you are, you can do the rest of the processing. So, now, so we assume that there are n basis functions which span the signal space. Each of S m t, so S m, m equals to 1 to capital M, indicates the different waveforms. Each of the waveforms can be represented as a linear combination of f and t. So, this is what we have explained. That means, each one of these waveform That means suppose I have a waveform, let us say this, or I have another waveform which is this, or I have another waveform which is of a different phase altogether. So, right, each of these waveforms could be represented as a linear combination of this basis function, where the component of this on this basis would be used to represent it in the vectorial form. So, in case of noise, that is important, f and t do not span the noise space, that is clear, because noise has a bandwidth which is infinity. So, if we think of bands which are orthogonal to each other. So, for instance, if I simply take this is the f, I divide it into orthogonal bands, this is not present here. That means, if I integrate this frequency with this frequency, they will produce 0, because this spans this space, this spans this space. So, if you take noise, it spans the entire space. So, with a limited set of basis functions, you cannot represent n t. So, that is all it says. Okay. But there is an important thing. It is true that noise outside the signal space is irrelevant to detection of the signal. So, that means, if my signal is present in this band of frequencies, all it says that the noise present in this band or noise present in this frequency will not influence the detection of the signal which is spanning this set of frequencies. So, this is the f axis, right. You can imagine it in this way, and if you are thinking in terms of basis function, it is an abstract way of representation, not necessarily connected to this. This is one particular realization. So, it also applies there equally. So, this is something what is important for us to remember. So, then what we talk of is, suppose r of t, that means the received signal, it passes through a parallel bank of n cross correlators, right. Why is it so? Simply because when we are projecting r of t onto the basis functions, we are as if correlating this signal r of t with each of the basis functions. The outcome would be the component of the signal on the basis function, and that is what is of our interest, that is the correlation value. So, this can be represented in a form that we have r of t. R of t is now split and sent to several different paths. So, it is being sent to several different paths. In one of the paths, r of t is multiplied by f 1 of t, the first path. It goes into the integrator 0 to capital T dt, and then it is sampled at a time t equals to capital T. So, let us see what happens. So, this effectively means that we have 0 to t integral r of t f k of t. So, k is 1 in this particular case dt. So, that means we are projecting r on f k, that means we are finding r of k. So, here what we should get is r 1 of small t, and at the sampling instant we are going to get r 1 of capital T. So, since this is r, in the next step you can expand r of t into SMT plus NT, because m is the mth waveform, right. So, this is how the expression looks like. We will look at what this yields, right. So, the left hand side could mean r of k. So, this one will produce r 1 of t, this line where r of t gets multiplied by f 2 of t, then integrated from 0 to t. So, by this expression k is equal to 2, and you get the value over here is integration of r t f k t over the period 0 to t dt, and that is equal to r of 2, and that is read at the time t equals to capital T. So, if you proceed in this manner, you have to do the projection on the n basis functions. So, we have talked about this n basis functions. So, this particular realization is as if you are correlating r with the different correlators, cross correlators, and these cross correlator functions are the different basis functions. So, you will be getting r 1, that is this result known as r k, r 2 up to r n, that is what we had started off with. This is what we had started off with. So, we wanted this, and this is simply how you get it, a pictorial representation of what we have been explaining verbally. So, when you realize this in circuit, the architecture could be realized in many different ways, that depends upon the optimization of implementation. But what it basically tells us is that you receive a signal, you need a multiplier, right. Multipliers are there in demodulators. So, what you have here is let us say cos 2 pi f c t, this is cos 2 pi f c plus another frequency maybe, or this may be sine if there are two dimensions, cos and sine, nothing else over here. If it is Emery FSK, it is e to the power of j 2 pi 1 delta f t, this one is e to the power of j 2 pi times 2 delta f t, and so on and so forth, right. So, now if you look at this particular expression which we had just explained, the left hand side is simply r k, k equals to 1, 2, 3, 4 up to n different dimensions, and integration of this term S m t with f k t is projection of the mth waveform on the kth basis. So, we write S m k. So, when we had written S of t earlier, we had described with S of t. So, here this is any waveform. So, m is the mth waveform, and projection on f k would produce the kth component of the mth waveform. So, that was represented in this structure. So, here remember m changes from 1 to capital M, different waveforms, and k changes from 1 to capital N, the different basis dimensions. So, we have S m k given by this, which is exactly same as the expression that we have here, right. If you look at this expression, is the same as this expression. So, it is the component of the waveform on the kth basis, plus there is this noise, right, which is the component of noise on the basis. So, noise is present all over, but we are correlating on a particular basis, or we are looking at a particular basis. So, that means we are trying to see what is the component of noise on that direction along which I am taking the component of the signal. So, wherever I am taking the signal on whichever direction, whichever basis, I am also getting the component of noise on that direction. Now, if there is no signal on a particular direction, that is not of my interest, whatever noise is there is not of my interest either, because I am not using that dimension at all. So, I am not using that dimension. So, intuitively you can think of, if I am not using the direction where signal should not be present, whatever noise is there should not influence me, because I am not looking at that direction at all. So, that is why we said at some point that noise outside the domain of the signal does not influence the decision criteria, right. So, moving further, we could say that the signal, the original signal, is represented by the vector S m with an underscore. I use underscore as a notation simply because making all those bolds bold fonts within the using hand notes is very difficult. So, I use underline to indicate vector in this particular discussion, and in different discussions, different courses, you will find different notations. Some people use an arrow on top, some will use a cap on top. So, we will identify at each location what do we mean. So, as of now we will continue with this particular notation, and with components S m k, reminding again n dimensions. Therefore, we could write r of t, the received signal, is equal to, so this is the received signal, do not get confused with what we had discussed here. So, here we had discussed the kth component, but now I am talking about the full signal. So, the full signal, how would you generate? You would sum r k multiplied by f k t, right, and that is what you have. So, r k is basically this. So, S m k and n k multiplied by f k. So, it is the same story. So, what we have over here, r of t is the signal with the projection, the coefficient and the signal added over linear combination over n dimensions, same with noise. However, we have a very important thing over here. Initially we said that n t is white Gaussian noise. Now, since Fk is limited, it does not span the noise space. So, there must be some amount of noise which is left, which is outside the signal space, that is n prime of t. So, n prime of t is beyond. So, that means whatever is n t, take away the projection of noise on the signal space, the remaining portion is n prime of t, right. So, this particular part is R k F k, because this is the signal and the noise what is received in the signal space and some amount of noise which is outside the signal space. So, n prime of t is defined as the extra noise which is not in the signal space. So, it is a zero mean Gaussian noise process, which is the difference between the original noise process and the projection of n t onto the basis function. And we have already said that it can be shown that n prime of t is irrelevant to the detector decision, and it can be decision can be made using r of k only, right. This we will see, we will show at an appropriate point. So, let us look at, so we will try to look at n k, and then finally we will develop the receiver further. So, the first property that we look about for n k is the mean value of n k. So, for mean value of n k, we use the expectation operator on n k. So, expectation operator of n k is n t multiplied by f k integral. Since expectation operator is there, we bring in expectation operation here. Now, E does not apply on f k because it is a deterministic function. So, E will apply of n t, E of n t is 0, you all know. So, therefore, this whole thing becomes 0, right. Okay. Next, we look at the correlation property of n k and n m, indicating the kth component of noise and the mth component of noise, right. So, we want to find if there is any correlation between these two components. So, for that we use the standard expression 0 to t because we have two different noise sources here, these two integrated. So, each integral having the variable dt and d tau, and n k is n t multiplied by f k and n m is n tau multiplied by f m. Expectation operator, it does not apply on this, it applies on this, right. So, now we know that E of n t n tau is delta t minus tau from our earlier discussions. That means, noise at two different instants of time is uncorrelated for wide Gaussian noise, that is what we know, and not only that, it is equal to n naught by 2, right. So, that means, for t equals to tau, this is equal to n naught, this term is equal to 1, that means, the correlation is n naught by 2, and t not equal to tau, this thing is equal to 0, right. So, that means, this integral is valid only for t is equal to tau. So, we have n naught by 2 and we set t is equal to tau, where it is delta and one of the integral goes away. So, we have n naught by 2, right, and delta is equal to 1 for t is equal to tau. So, we are left with integral 0 to t f k t f m t. Now, you can easily recall that since these two are designed to be orthonormal basis functions, this integral will be equal to 0 for k not equal to m and will be equal to 1 for k equal to m. So, that means, this can be represented as half n naught, that is here, and delta m minus k, which is equal to 1 for m equals to k and 0 for m not equal to k. So, what we have is the correlation between the two noise is equal to half delta m k, which means that these two noise components are uncorrelated with each other and hence are independent, because we have taken Gaussian noise, right. So, only for delta equals to k, only for m equals to k, we have the situation where this value will be equal to n naught by 2. So, that means, for E of n k squared, you have n naught upon 2, that means, the variance is n naught upon 2 and the mean is 0. So, again we have a white Gaussian noise, we have Gaussian noise with mean of 0 and variance of n naught by 2. So, Therefore, we can proceed and state that the expected value of R of k, we did expectation of this, we did correlation of this. Now, we move to find expected value of R k. Expected value of R k would be expectation of R k expanded over here, right. So, kth component mth signal. Now, this is a deterministic value, we know the fixed value of it, it is a coefficient. So, expectation operator when applies on this is the value itself, and E of n k you have seen to be 0. So, therefore, E of R k is that of S m k. What does it mean? It means that the expected value of the kth component of the received signal is the kth component of the transmitted signal. So, that means if I have sent D, suppose I have D and minus D, and suppose I have sent D. So, the expected value would be D even though it is corrupted by noise. So, let us have a look at it. So, our transmitted signal would look like this. So, this is D, this is minus D, right, and suppose we have this. So, it says that suppose I am sending only this signal, right, only D, noise would be added on top of it. Since noise is 0 mean, right, expectation would be same as D. So, it is as simple as that, right. And if you think in terms of QAM, there is a constellation, there are two projections on these two axes. So, noise will affect the I axis, it will affect the Q axis. So, this received signal could go in any space, but on an average if I am sending this constellation for a very large amount of time, then I am going to get the average value of the received signal as this particular point, the mean value. So, there will be fluctuations in this direction, there will be fluctuations in this direction, but the mean value will be the same as this, right. So, what we have is n k, we have n k are uncorrelated Gaussian random variables, and therefore, we have already stated that they are statistically independent, we have already stated that. So, R k conditioned on the mth signal transmitted, that means, if we have a particular m signal that is transmitted, would also be statistically independent, because R of k is equal to S m k plus n k, which has a mean m k and it has noise added to it. This has 0 mean, this is a fixed value. So, that means, R k is a random variable which is distributed according to n k, but has a mean defined by this, and that since it is distributed according to n k, it will also have the properties of n k. So, it is also, these are also statistically independent, right, and conditioned on the mth signal means given that you know the particular signal. If you take this as random, then of course, results would be different. So, we have R of k being equal to S m k plus n k. If this is given, that means the mean is known, then R k is also a Gaussian random variable with mean of S m k and variance of n naught by 2 as per this. And then we could write that the probability density function of the received signal vector R, which is made up of k components, k equals n components, k equals to 1 to capital N, given a particular signal, is the product of the individual or the marginal densities P of R k, that means the kth component given S m. So, S m means S m k. So, what we have over here is that since these are statistically independent, the joint distribution of these components of R turn out to be the product of the marginal distribution. So, we have used that. If we did not, if we could not state that these are statistically independent, then we would have had to find the joint distribution of the k components of R, right. So, R is made up of R 1, R 2 up to R n. So, when we say PDF of R given S m, so S m is also having components S m 1 up to S m capital N. So, this vector conditioned on this vector, we should have a joint distribution, but since it is statistically independent, it is a product of the marginal distribution. That means, you can simply work with each of the component independent of the other component. That is what it says. So, where the P of R k given S m k, since we know from this that this has the PDF of N k with a mean of S m k, what we have is the Gaussian distribution 1 over root pi n naught, because there is 2 pi sigma squared n is n naught by 2, 2 and 2 cancels. So, we have pi n naught e to the power of minus x or r k minus mu, or the mean is S m k squared upon 2 sigma squared is n naught by 2, 2 and 2 cancels, you are left with this. So, if you substitute this back in this expression, you are going to get this capital N times, because there are n times multiplication. So, this is raised to the power of n, there is a square root that comes as half, e to the power of this multiplied pi times, that means in the exponent we are going to multiplied n times. So, in the exponent you are going to add them up capital N times. So, you have minus summation r k minus S m k squared upon n naught. Now, this is a very important expression that we have arrived at. So, we should be carefully noting this, because in the next discussion we will take advantage of this particular expression, that what we have arrived over here to derive our receiver, which is still to be developed. So, please note that the way we are deriving the receiver is by starting with the signal model, adding the effect of channel, then the projection of the signal on the different components, trying to understand the statistical properties about this correlation about these components, and then given the received signal conditioned on a particular transmitted signal. So, we are looking at the joint probability of these components, which interestingly came out to be statistically independent, and we have arrived at that particular expression of probability. So, we will be using this expression to derive some kind of a receiver, which will be clear very soon. Thank you.